see. Okay, thank you very much for giving me this opportunity to talk about just-in-time scripting for design. I borrowed the name just-in-time scripting from just-in-time manufacturing, which is also called Toyota Production System and originates from Toyota during 1960s. Just-in-time manufacturing is a methodology aimed primarily at reducing times within the production system, as well as response times from suppliers and to customers. The system evolved out of circumstances that Toyota faced, requiring the production of small quantities of many varieties in low demand. Now let's talk about scripting for design. When you look at the architecture project, each project is very unique. In my experience, there was no single project that was the same as the previous projects. For any architecture project, project team members are really important element. Architects, designers have their own ways to design. They want scripts or tools to work for them, not the other way. Because each project is unique, it needs varying levels of customization in its workflows. In fashion industry, we know two terms, haute couture and pret-à-porter. Every haute couture piece is made to measure for a single client or just few people. On the other hand, pret-à-porter or ready-to-wear fashion are made for many customers in different sizes. When you think about architecture projects, they are much closer to haute couture, not ready-to-wear. How can you customize our workflows with shifting priorities for different projects? We find that the development of scripts in our projects needs to be more like just-in-time manufacturing because we need to respond to demands quickly and customize workflows to fit each unique project situations. Um, Just-in-time scripting is based on demands. It requires the development process to be fast and simplified. We also need to identify repeating elements in scripting to rationalize the development in the future. If we look at design production, comparing design processes with the scripting to manual design processes, designs by scripts feels slower than manual designs in the beginning. Manual design processes are pretty much linear in that you see results in real time. On the other hand, design production by scripts is more like a step because design production seems pretty flat during scripting. Um, Once you reach to a point when you can explore numerous designs with the scripts, then design productivity easily surpasses manual design processes. Reducing scripting time is very helpful in developing scripts or tools for projects based on demands so that design productivity surpasses manual design production early in the design process. In order to make scripts effectively just in time when they are needed, we try to identify repeating parts in our scripts and package them as part of our grasshopper toolbar. We have currently more than 170 user objects in our SG toolbar. And most of them are clusters and snippets. And we also develop plugin components. In a very similar manner as automobile manufacturers share modular parts in manufacturing different car models or even different trims within for the same car model. We use modularized scripts in making various scripts effectively. With this intro about just-in-time scripting, I want to use 3 projects to show unique design aspects of each project and how we develop the scripts or small tools to support design processes effectively. The first project is a Virginia Tech Innovation Campus academic building. Virginia Tech is setting up a tech-oriented campus in Alexandria, Virginia, the south of Washington, D.C. This building is the first to be constructed in this new campus. The design has many sustainability features, and one of the main design focuses was to maximize electricity generated by photovoltaic panels on roof and facades. To achieve this goal, we used a generative design approach to optimize its massing. Um, I'm not going to get into details of the process, but we used multiple generative models as illustrated in this diagram. The generative models flex the building geometries within the zoning envelope, generating hundreds of design options with metrics to measure each design's performance. We used the Discover Grasshopper Discover plugin. It generated this scatter plot with design options. Each dot in the scatter plot is connected with a design option. In this scatter plot layout, x-axis is floor area differences between the target floor area and design options. So the smaller the number, the better the design option. Y-axis is total radiation on PV surfaces. So the higher the number, the better the design. So using this scatter plot, we could identify high-performing design options gathered in the upper left corner inside the red dash circle. Once we pick the design typology, we refined it further with the final third generative model. So all these design options evolved over generations, and we picked number 581 out of 630 designs as the best performing typology. The selected typology gets 25% more annual radiation on photovoltaic surfaces than a base model without facets. It also minimized the building envelope surfaces, hitting the target floor areas. Based on the selected the typology, we went through numerous iterative processes to develop facade designs with rigorous daylighting analysis. Facade design varies depending on orientation, and geometries are fully controlled by grasshopper scripts. The south facades have a building integrated photovoltaic panels as a main design element. South facades have horizontal laminated photovoltaic glass fins set at different angles depending on surface angles. This rendering shows both the south and southeast facades, the entering point of the campus. West facade is comprised of vertical angled fins at varied depths and free glasses on split panels. The rendering shows both this west facade and the south facades. East facade design is pretty similar to west facade. It's just vertical. The fin angles are set at different angles. This rendering shows both the west and north facades. So we used the several clusters developed from previous projects. So that way we could reduce initial scripting time and make grasshopper definitions cleaner. We use the grasshopper geometries for Revit facade models, and we needed to develop a new C# component to control cutting frame offset distances differently on all sides from cutting grease. This new component also include trimming function and outputs trimmed cotton wool panels, frames, and even back panels for shadow box. It also has an option to make frames parallel to floors or perpendicular to panel surfaces. We believe we can use these new components for many other projects in the future. The second project is the U.S. Coast Guard Maritime Center of Excellence. It's a multi-purpose building accommodating a welcome center, a classroom, a boat shop with engineering labs and offices. The client wanted to create an iconic image with this project in the campus. Its design is the expression of sails and sleek hulls inspired by the maritime heritage of the institution. Um, we needed to create a dynamic roof form from a very simple geometry in order to meet the project budget. So we created this series of arcs as a starting point and got points on arcs and created curves by connecting those points on arcs. That way, we could create this trimmed bearable surface from simple arcs. So the final roof geometry looks complex, but it's actually driven from very simple geometries. And we got the wall surfaces driven from roof outlines. We split those wall surfaces into glass and metal panel surfaces, roof frames, ceiling planks, and the roof panels all driven from roof geometry. The design went through multiple iterations to optimize roof geometries and plan outlines. This project was before Rhino Inside Revit came out. So before this project, we used the various methods to transfer geometry data from Grasshopper to Revit. During this project, we standardized the geometry transfer methods by creating Grasshopper components to export data to Excel and making a dynamo player graph to generate Revit families. So this short video shows how it exports the geometry data from Grasshopper to Excel and then generate Revit families in Revit using dynamo graph definition. I'll just skim through the Revit documentation sheets. This is the work points for facade panels, work points for roof geometry, the work points and work points for glue lamp beams and detail drawings, and coordinate tables for all the work points, roof assembly section drawings, and then this is the rendering from water side and the rendering from the entry point. So after finishing this project, we refined the process to standardize geometry transfer from Grasshopper to Revit. We named Geometry Revitizer. It was to simplify Revit documentation for projects using Grasshopper scripts. The last project is Wanxiang Innovative Juneang City project. It's a master plan project at city scale. The site is located on the south bank of the Hangzhou, China. Because the project area was huge with a total land area of 10,000 square kilometers, we needed a way to create 3D meshing quickly from 2D block outlines to make a guide model with the target gross building areas. Our approach was to make Grasshopper scripts that would generate different types of meshing using 2D block outlines. This is a courtyard type, and this is the mixed use type. We also had several other types for building types. Scripts also control skylines based on central locations. So if you move central business locations, then the skylines would adapt. This short video shows how the overall massing was controlled using attractor points for one area of the site. So you move around these attractor points, and then the skyline would change. And so this way we could bake the model and then develop it further. This is a prototype of a tool applying similar logic with a human UI user interface. So you set target FAR and you simulate the models by applying different building types and the height, and the model gives you the area data. And that way you could simulate the model quickly and to get a target model with the appropriate the gross building areas. So these are so this is the some final renderings of the project. Again, we modularized the scripts in making grasshopper scripts for this project. We developed the clusters as shown in the upper part of this page during project hours, and then make plugin components to refine them further after finishing projects. As I showed in these three project examples, every project has different design processes based on its own priority. We customize computational design methodology to fit each unique project with rationalized pre-made parts as one way of multi-threaded approaches to expand the use of computation in our practice. With that, I'll end my presentation, and thank you very much.